Apart from ray tracing, almost all games use one foundational way of rendering: software rasterization. It is a complex work of trigonometry and other math to transform 3D coordinates to draw onto a 2D screen, which I do not understand. So let's change that. A year ago, I decided to attempt to learn the basics. I wanted to make a 3-dimensional version of the old game Snake. And of course, I wrote it in Java, with which I was obsessed with at the time. Of course, today my stance is that any language except C is obsolete. However, back then I just enjoyed programming in Java, due to which, to this day, it still holds a special place to me. The logic within the code base is rather standard. The only notable thing I would mention is that it technically doesn't run at 60 frames per second, but instead its frame rate is dependent on how fast the snake moves. Considering it moves every 500 milliseconds, this means that it moves twice per second, meaning the game runs at 2 frames per second. Although for once it isn't because of the language or because of my incompetence. Of course, this project was to a very large degree made by LLM-powered autocomplete. I think it's quite obvious when seeing that I have a comment saying that I convert something to radians, documenting the next line, which literally uses the function math.toRadians. Now I can simply run this by navigating into the directory with my compiled Java binaries and running java main. These white segments around the rendered area are because the program expects to be able to set the window size, but Wayland says no, so it just fills the rest with white. Now yes, this is 3D, but it does look quite odd, and you have no sense of perspective. The reason for that is that this is not 1 or 2 point perspective, but isometric perspective. On 1 point perspective, if you were to render a rectangle-based prism, you would have a rectangle from which you would draw a line from each corner to point in the center of the screen. From there you would measure on each line for the depth the object is supposed to have and cut it off there. After which you would connect the remaining lines and apply some coloring so you don't see the lines in the back in the front. In 2-point perspective, you would do something similar, where you instead just draw one vertical line, draw 2 connections from each end towards the respective point in the image, and cut them off based on width and depth. From there, however, you take the cutoff points and bring them towards the opposite points and cut them off where they intersect. This is technically the more realistic perspective, as we humans
Hello there, fellow humans.
have 2 eyes, which means 2 points. The last perspective I will be explaining is the one I have used here, isometric perspective. This isn't really used in art, but rather in product design and such. It works off of having only 3 different types of lines, where the only variation is length. A vertical line, a diagonal line to the top left, and lastly a diagonal line to the top right. So a cube is just a collection of 3 vertical lines, 3 diagonal lines to the left, and 3 diagonal lines to the right. There is no perspective except rotation around the object by 90 degrees. So to position cubes like this, all I need to do is first follow one of the diagonal lines for how far the cube is positioned on the x-axis, then on the other diagonal for where it is positioned on the z-axis, and finally vertically for where it is positioned on the y-axis. Of course, the visible issue with this is that there is no way for the player to tell how far away something is. As while some coloring was implemented so the right things are in front of another, there is no way to tell how far something is behind something else. Despite this, I also decided to implement this in P5.js, so I guess I also have it as a website now. Yes, this version is quite buggy. No, I do not intend to fix it, because I instead want to do what I always do: rewrite it in C for optimal performance. Optimal excluding my inoptimizations, and writing it in Vulkan, which would make it significantly more efficient. Now to set up the project, I could just copy over the code from the upscaling program, but unlike last time, I do not have any excuse why I'm not using STL3, so just for the one person who commented on the upscaling video about that, I will be starting fresh with STL3. Now the difference is quite simple. I just used the -l STL3 flag instead of the -l STL2 flag. Then at the top of my main.c file, I define STL main use callbacks to be set to 1, so STL knows I will be calling some of its functions instead of making my own render loop. These STL functions include STL app init, which I use to set some of the metadata, initialize STL video, create a program window, and initialize my snake. The next STL function being used is STL app event, which I use to quit the program when the user tries to close it, and to process left, right, up, down, forwards, and backwards. The last function being used is STL_app iterate, which, as you guessed, is called every frame. In here I just have a mechanism to run a tick every certain amount of frames. The reason I do that instead of just capping the frame rate at my desired tick rate is so when I resize the window, it doesn't take half a second for it to fill in the background. Then we clear the window, render the game state, and wait for about 40 milliseconds, so we have about 30 frames per second. Now, because this is the 3rd time writing a 3D Snake game, and probably at least the 7th time of writing Snake at all, it went rather quick. If you want the details of writing the logic for Snake, just watch the Java video where I cover those. The only difference is that I account for 2 more directions and change the way rendering works. Speaking of, I think it is time I finally tell you how rendering actually works. After consulting the LLM, it turns out it is quite simple. There are 2 main things you need to remember. The x-axis is defined by cosine and the y-axis by sine. That didn't tell you much? Okay. If I want to render a cube in isometric, I go as follows. I get the bottom corner's position on the screen, and then want to draw the 3 lines drawing from it. The way I draw them is that the y-axis is of course just drawing upwards. Simple. However, the other 2 directions of the cube I need to apply these mathematics. To the left, I need to know how far left in 3D space, and then also this angle. Then, to get to the position of the end of the line, I take my origin, and on the screen space x-axis, subtract the cosine of the angle multiplied by the length of the edge in 3D space. Then on the y-axis in screen space, I just do the exact same thing but use the sine instead of the cosine. To go to the right, it is the exact same thing as for going to the left, except that we add the cosine on the x-axis instead of subtracting it. From there, to complete the cube, we draw 2 vertical lines for both of these endpoints, connect the ends of the vertical lines, and finally draw a diagonal line to the right from the left and vice versa. But all of that and more in math aside, I think it is time for something more interesting. More complicated math. I don't want to leave it at having made an isometric 3D snake. For the last thing today, I want to be making a 3D snake with 1-point perspective, so there is some sense of how far away something is. Fortunately, I can just copy over the 3D snake project from just now, and just need to revise the way I render a frame. So to draw a cube, we need its position in 3D space, the length of all sides, and its color. Then we calculate the coordinates of the corners and run them through this formula to convert them to 2D coordinates. Then we combine this with the color and whatever the 2 ones over here are needed for into an STL vertex, which are all put into a list. Then we make another list. This one describes which pairs of 3 vertices should be considered a triangle, to finally be rendered using STL_render geometry, and the last thing remaining is drawing the connection lines. Now all that remains is backline coloring, so we don't see the back edges on the front, and the 1-point perspective version is done. Unlike the upscaling project, I will not be doing the benchmark, as all I could test is how fast the frame is rendered and how fast the language is at casting integers to floats, vice versa, multiplication and division. And finally, instead of drawing out the video any longer, I will leave it at that. As usual, the project repository for the 1-point perspective snake is in the description in case you are interested. There you should also find a link to the isometric snake website and the code. I think it would be interesting to someday also try to make a crude ray tracing algorithm, however that will of course need to wait until I'm significantly more knowledgeable on all of this. I guess it's one of the things to add to my list of things I want to at some point be capable of, including actually learning how to use a graphics library, like Vulkan or at least OpenGL. If you have enjoyed listening to me ramble about code, then I'm sure you will also enjoy watching this video in which I made a website which infinitely generates somewhat coherent music. Or if you have already watched that one, then I invite you to watch my video about making an upscaling program. And now, with all of that said, all that remains is for me to say thank you for watching.